It's not light away.
Yes. They're probably going there.
Yeah.
Oh. This way. Wait.
Alright, also before we get started, feel free to come up front. It'll make it easier for us to help you throughout the challenges later. So we're gonna start with so let's give you a second to get the flag in. I mean, we'll post the slides later as well, so you can just copy it, but yeah, it should be easier. Okay. So what exactly is PWN? So maybe a more descriptive name would be binary exploitation. So kind of what does that mean? Like a binary is what we call a compiled program. So what we're taking advantage of is not sort of the abstract idea of what our code is doing, more so what it actually gets compiled down into and how it's being executed on the machine itself, so like on your CPU. So most like really valuable exploits actually kind of fall under this category, which makes it really cool. But because they're really valuable because it's hard, right? So feel free to ask us for help because there's kind of a lot going on, right? You need to understand not only the C code, you need to understand the assembly, the memory model, and multiple representations of the data that you're looking at. So there's kind of a lot going on. So feel free to ask us for help. And then if you don't need help, please help out people around you. It's also become help. So let's start out with kind of what memory is, right? So in some sense, the reason we call it binary is because it's literally just a sequence of bytes, right? So each number is stored at an address on a 64-bit platform, like what we're going to be talking about today. It's 0 to that, which is the maximum 64-bit integer in hex. So you can think of it just sort of like as a massive linear array of memory, right? It's like a list of bytes. So those bytes that we're talking about, they can either be instructions, which is like x86 assembly instructions, or it can be data, which has like special meanings. So think about like, an integer, constants in your code, strings, stuff like that. So this is sort of the overview of the memory layout. So up at the top, we have text, which is that actual like program code, the instructions that you're running. The data, which is globals that have initialized values, ESS, which is data which doesn't have initialized value, globals. And then below that, which is a little bit more interesting because it's more dynamic, is the heap, which goes downwards, and then the stack, which goes up towards the lower addresses, the runtime data. And for this, we're really interested in the text, which is where all the, again, the program instructions lie, and the stack, which is where like all your function calls and the local variables to those functions are stored. So now let's go in a lot more detail about the stack, right? So this is how you call a function, right? In C code, we maybe have those 3 parameters and then the name of the method. So when you get started here, you'll put the arguments in. This is like kind of what you do before you call the function. You want to make sure all your arguments are the correct registers because that's how the function will retrieve those parameters. And now let's talk about kind of the memory, right? Which is where things are more interesting. You can like nest function calls, stuff like that, where a fixed number of registers, you really can't do that. So like, let's say before we had some stuff on the stack, maybe we were calling some other functions, maybe something else is going on, right? And also in this diagram, we're gonna have the high address at the bottom, low at the top. So at this point, the stack pointer is at the very top of the stack, as it always is. And let's say that we were in some previous function call where the base pointer is somewhere in this. We'll talk more about the base pointers later. When you okay. I guess we use the side. Oh, never mind that. All right, so when we actually call the function using the call assembly instruction, what it'll do is it'll push the return address, which is where we were before we called this function, onto the top of the stack. Because we pushed it, we need to move the stack pointer up again to where the top of the stack is. This will take up 8 bytes, which will be useful later. And then when we call, where we actually enter the function, it will be inside the function itself, maybe an enter instruction or some prologue, which will do the following. It'll add the base pointer, which is where this was before, to the top of the stack, which will also take 8 bytes because it's 64-bit. And then, yeah, the stack pointer is moved up again. But now, also, the second part of the prologue will move the base pointer to the current top of this, because the base pointer, what's supposed to be, is supposed to be kind of the bottom of our stack frame. So this is where kind of everything is referenced off, because the stack might move up or down, but within a function, the base pointer is always where it started. So now, let's say we, in our execution of the function, we add some more local variables to the top of the stack. They would just go up here. Let's say we do some more, they just keep going up, and the stack pointer keeps moving up with it. Base pointer stays in place. now let's say we're done, we're getting ready to exit. We have like a function epilogue or maybe leave instruction. What it'll do is it'll set the stack pointer back down to the base pointer. So all these local variables are now above the stack pointer, which means they're kind of out of scope. And then what we do is we set the base pointer, like this previous base pointer that we had from our previous call frame, is now going to get saved, as going to get set to this value that we saved on the stack earlier. And then the stack pointer again, because we just pop this off, is moved down. And then now when we're finally returning, calling the ret instruction, it'll move our code execution, which is the instruction pointer, to the save return address. And now we're back in whatever function we originally were before we called this. Now everything's been torn down. So kind of in summary, this is what we had going on. We saved the arguments. We put the return address on with the base pointer to the previous frame, which was down here. And as we were executing with the local variables, and we tore it all down and went back down. Now we'll talk about smashing stack.
Okay, so first of all, that was didn't like quite get all of that. It's okay. You don't need to understand that completely to be able to code some programs. So next we'll talk about that. Okay, so here's an example program that may have something wrong with it. Does anyone here have an idea of what might go wrong with this program? Well, okay, so the main thing that is probably like unexpected with this program is this gets call here, which we'll talk about, has some, like you should never use that function, but let's talk about what the gets function is. So this is our vulnerable function of the day. The gets function just writes like a string, our writes input to a buffer or an address as provided. And the reason why this is dangerous is that it doesn't check, there's no limit as to what or as to how much it writes to the buffer. It will write like as much input as you provide. And so we'll talk about how that can be dangerous. Oh, wait. Yes, okay. So here's a function. Let's say we provide an input 8 A's and 8 B's. What do you think will be printed by the function after we provide that input? Puts prints a variable. Does everyone have any ideas? 8 B's, yes. 8 B's will be printed. You might think that might be strange, but the reason why is because when we send those 8 A's and 8 B's and we place it into the stack var 2, which is on the stack, that stack var 2 is only 8 bytes, so only hold 8 characters. So the rest of the characters will actually overflow into the next variable onto the stack. So it will look something like this. So then when we put stack var 1, that will print 8 B's. And so now we'll talk about a little bit about why this can be very dangerous and how attackers can use this to sort of hijack control flow in your program. So now we'll go back to the return address, which is what Jake talked about previously. And here's an example of how the return address kind of works. So after we call the vulnerable function, let's say like the next instruction after that vulnerable function call is at OX1004. So when it calls the vulnerable function, it will push OX1004 onto the stack, and so that once that function is over, it will return to that address. So it will end up going to that puts call afterwards. But if we can like sort of overflow a variable on the stack, and remember our overflow direction goes downwards, we could possibly overwrite this address. So that's what we'll talk about. So this is how we can redirect control flow. So let's say we send 8 A's, 8 B's, and so let's say that we have a win function that's at that address. That's commented right there. We can send like 8 A's, 8 B's, and that will populate the stack var 1 variable and the save base pointer respectively. And then when we can override the return address to any address we want. So it will look something like this. where we set the return address equal to the address of the new function that we want to jump to. So now vulnerable, instead of returning after the function call, instead of returning back to where it came from, it will return to any function that we want to call in the program. So next, we'll just talk a little about integer overflows. So in C, like integers are stored with a fixed number of bytes. So there's like a maximum number that the integer can store. So if you like try to increment past that or something like that, you'll actually wrap around to a negative number or to 0, depending on whether the integer was signed or unsigned. And so actually a lot of times this can be used to achieve buffer overflows or buffer underflows. Like if you like overflow an integer to a negative number, then you can index backwards in an array, which could potentially cause some problems. Next, we'll talk about delivering an exploit. There's a bunch of tools that we can use to make exploitation easier for Pwn. So first of all, actually, I want to talk a little bit about endiness. So when you attempt some of these challenges, they'll print like a little visualization of the stack for you to better understand what's happening in your program. And some of the numbers you'll see, like some of the variables that are initialized to a number, it will appear backwards on the stack. And the reason for that is because of little endiness. So basically what this means is the least significant byte of an integer or a number is stored first, or like at the lowest memory address. So like for this hexadecimal number here, it will be stored with the byte 0x88 at the lowest memory address and 0x11 at the higher address, which is a little bit counterintuitive, but as you work with it more, you'll get used to that and it'll feel like second nature actually. Next, sometimes like we talked about jumping to a win function, but like you need to get the address for that function sometimes. So an easy way to do that is you can either use a tool like object dump. You can grep for, like in this case it's grepping for main, but you can grep for any function that you care about to get its address. You can also do it with GDB as shown here, or in bdrup, but probably do it with object dump or GDB. It's probably easier. And for setting your exploits, we'll talk about a couple things. First is echo. Echo is probably shown to be used if you're trying to do something simple, but here, if we talked about before, if you saw one of the earlier slides where we wanted to send an address or like overwrite the return address with the address you control, but sometimes those bytes that are part of that address aren't like, we can't manually enter them into the terminal the same way you can like type characters or something, or like letters. And so a way to be able to send that to the standard input of the challenge is through, you can do echo-e so they can like use escape codes to send those bytes. But what you probably should use for most Pwn challenges is this really cool library called Pwn tools. It allows you to you can run local processes and connect to them. You can connect to remote processes like the challenges, and you can receive and send input, and you can even drop an interactive shell. So once you're done with your like exploit, you can like you can interact with the program afterwards. So yeah, here's just an example. Like we can define the like the address of a win function that we want to overwrite the return address to, and then we like overflow. We can define an exploit, and this P64 function is really nice because it packs an address into that like little endian byte format, so you don't even have to worry about that. And then you can send the exploit and drop an interactive shell. That's usually the format for what the solves for most of these challenges will look like. And there's a starter file in the first challenge, so you can use that to work with the challenges. Yeah, then here's a way to do it locally. Like you can even actually open or you can run the process locally too if you want to just run it with a local binary. But also you can, even if you're doing it locally, you can also attach GDB to that process. So sometimes when you want to debug something in a program to like kind of trace your exploit and see how your exploit is like messing with memory or something like that, you can actually attach a debugger to it, and that'll allow you to make things a lot easier. And yeah, here's just a cheat sheet for some of the Pwn tools commands that you will find useful, like sending and receiving input, packing integers, even like you can like creating like PWN has a special object called elf, which like you basically just think of it as an object that represents your binary. And so you can use it to make things, has a lot of convenience things associated with it. And yeah, all right, so here's some of the challenges you can do. There's integer overflow, which is a basic integer overflow. There's bug bounty 1 through 6, which are each like stack challenges of increasing difficulty. Bug bounties 5 and 6 will require knowledge, or 5 will require knowledge of shellcode, and 6 will require knowledge of format string vulnerabilities. Both of which will be covered in PWN 2, but if you're feeling brave, you should attempt them now and feel free to ask any questions. And then Pony Mart is another great challenge that we have. Yeah, and as I said before, bug bounty 1 through 4 print a visualization of the stack. But that isn't usually the case. So bug bounty 5 and 6 won't do that, and most PWN challenges won't do that. So usually you'll be using GEB or something similar to inspect the memory yourself. And yeah, next meetings, this Thursday we'll have Crypto 1 with George and Nico. And on Sunday we'll have Crypto 2 with Richard and Emma. And the next Thursday will be Halloween. So yeah. Yeah, and here's the meeting flag again if you need it. And yeah, get to solving challenges. Feel free to ask any questions. And also, if you have an Apple Silicon Mac and you're confused on how to be able to run these programs because you won't be able to run them natively, raise your hand and I can come over and help with that. But yeah, thanks everyone.